Alright, welcome back to another instructional video for this course. We have been talking a lot about atoms, and specifically we've been talking a lot about the subatomic particles in an atom. We've been talking about the neutrons, and as the number of neutrons changes for a particular atom or an atom of an element, we know those are called isotopes. We've also been talking about electrons, and if the number of electrons changes for a particular atom of an element, we know those are called ions, and they form charged particles. And we talked about protons. We know that a proton is the unique identification for a particular element. That number of protons is never going to change for that particular element. So every element has its own unique number of protons, and it's fixed. As long as that number of protons stays the same, it is always going to be that same element. Neutrons can change, electrons can change, protons never change for a specific element. That is its identification. Okay, also called its atomic number, if you recall. Well, we're going to zoom in a little bit more on the topic of electrons, and we're going to focus on electrons a little bit more as we move forward, because it is the electrons that are involved in the bonding of one atom to another atom. And in particular, it is the outermost electrons, those are called valence electrons, that are involved in that bonding. So let's talk a little bit about electrons, and this unit, or this particular video, is going to be looking at electron energy and light, and you'll see why it's connected to light in just a moment. So we're going to be answering this question: how does light reveal the behavior of electrons in an atom? We really want to look at how electrons behave. What is it that determines where they reside, how they interact, and as we learn, or as scientists learn more and more about light, that helped us understand a little bit more about the electron. Okay? So the color of light is useful in finding out what's in matter. Here's why. The emission of light by hydrogen is a gas, and other atoms has played a key role in understanding the electronic structure of atoms. Electronic meaning how the electrons are arranged, the structure, the arrangement of electrons in an atom. Trace materials, such as evidence from a crime scene, lead in paint, or mercury in drinking water, can be identified by heating or burning the materials and then examining the colors of light given off. So, we're going to be talking about how every particular element or particular type of atom is going to emit a specific type of light. And we'll talk about why that is as we identify the structure of the electrons in an atom. So here is model number 1, and it is all about white light. Here is white light coming from a light bulb. It is then shown through a prism. It is split into the different individual colors here. You probably have heard of Roy G. Biv before. And these are the energies, the wavelength, and the speeds for all those different colors. Okay? Energy is measured in joules, that's why there's a J here. Wavelength here is measured in nanometers. Wavelength, basically, wave, you probably know, travels in a wave pattern. The wavelength would be the distance from peak to peak on that wave. And the symbol for that would be like an upside down Y symbol. Okay? So that right there is called wavelength, and then the speed is how fast it is traveling, and that is measured in meters per second. How many meters does it cover in 1 second? And you'll notice that all of these speeds are identical, because all forms of light or all forms of electromagnetic radiation are going to travel at the same speed. It's called the speed of light, and that is 3 times 10 to the 8. That's a huge number. That many meters every second. That's astounding. Okay, that's staggering. So let's look through the questions here. Number 1 says, trace the arrows in model 1 and shade in the table with colored pencils where appropriate. You don't need to do that necessarily, but basically they're just showing you that white light, when you divide white light into the different colors, you're going to get reds, oranges, yellows, greens, blues, and violets. You can take the time to color those if you want to, but certainly not necessary. What happens to white light when it passes through a prism? So this is going to split into colors. And specifically when I say colors, what I'm really saying is it's going to split into these different wavelengths here. Notice there's a range of wavelengths. So reds, notice it's plural, doesn't mean it's just one red, but it's a shade, a range of shades of reds. And the wavelength of those reds goes from 625 to 740 nanometers. Okay? Why are the colors labeled? Why are the color labels in the table in Model 1 plural? I just kind of mentioned that. So reds means that there is a range of reds, for example, or a range of any of the colors. It's not just a specific red or a specific orange. There is a whole range of those different colors within that category. All right, and do all colors of light travel at the same speed? Yes, they all travel at 3 times 10 to the 8 meters per second. Do all colors of light have the same energy? No, they do not. Let's look back up at Model 1. These have different energies called photon energy. Photon, just think of photon as a packet of energy, a packet of light energy, okay? And they have different amounts of energy. These are measured in times 10 to the 21 joules. That sounds terribly small, and it is, but we're just talking about one tiny little packet, a little ball of light energy measured in how many joules of energy, okay? So they don't all have the same energy packet that they're carrying. Which colors have the highest energy and the least energy? So if we look at this, the highest energy here is going to be your violets at this range. So this would be high energy here. This would be lower energy down here. Reds are the lower energy. Consider the light illustrated in Model 1. Which color corresponds to the longest wavelength? So which color has the longest wavelength? Longest wavelength is right here. Those would be your reds. And which color corresponds to the shortest wavelength? That would be your violets. Okay? Shorter wavelength is down here. Write a sentence that describes the relationship between wavelength and energy of light. Okay, wavelength and energy of light. So notice if you have long wavelength here, this is long wavelength, this is a short wavelength. Short wavelength means high energy. Long wavelength means low energy. So that's called an inverse relationship. And as wavelength increases, as wavelength goes up, the energy actually is going to go down. Okay? Or you could say high energy is shorter wavelength. Let me just take a moment, all right, and just kind of give you maybe a little bit of an illustration to help you remember this. You can think of waves kind of like cars in traffic. Okay? If you have cars traveling down a road, these are cars, by the way, sorry for my poor artwork. So you've got lane 1 here and lane 2. In lane 1, you've got traffic flowing at 50 miles per hour. Okay? If the cars are really close together, that would mean you have a short distance between those vehicles, and that corresponds to a short wavelength. In lane number 2, the cars are also traveling at 50 miles per hour, but they're farther apart. That has a longer wavelength. So which lane is more dangerous to cross? Well, hopefully you understand that if they're traveling at the same speed, if the cars are further apart, you have more time being able to cross that lane, and therefore it is less dangerous. So this is the lower energy, less dangerous. If the cars are close together, it's very hard to get across that lane in between those vehicles when they're traveling at the same speed as in lane 2 because the cars are closer together. So this is high energy, dangerous to cross that lane. A short wavelength means you've got high energy. A long wavelength means you have low energy. Okay, so I hope that illustration is helpful. Here's Model 2. Now Model 2, just kind of like in Model 1. Remember Model 1 was white light, and white light was then being shown or directed through a prism, and it is going to split. That piece of glass right there is going to split this white light into the different colors. So in a similar fashion, we're going to take light, and it's going to go through a prism, and it's going to be split. But this light now is not white light. It is light that is being emitted because we have a gas in this tube right here. It's hydrogen gas. It's a hydrogen gas, and that gas is being excited because there's an electrical charge that is being passed through that gas. So what's happening is the electrons are getting excited, and as those electrons get excited, they go to higher energy levels, and then they lose that energy, they drop back down, and when they drop back down, they emit light. Okay? They gain energy. This is the electron. They gain energy from the electricity in this case. And then when they lose that energy there. They lose that energy, and when they do, they emit light. So this light right here that is coming from this tube, this hydrogen tube, is light that is being created because of the energy, or the light energy, really, the light that is being emitted because the energy is being transferred from the electrons to light energy. So the electrons lose their energy after they've gained it. They lose that energy. They drop back down to a lower energy position, and when they do that, they emit the same energy that they gained, but they emit it in the form of light. That light then is going to pass through these slits, just kind of narrow it down, and then through the prism, and it's going to split. But notice we have very distinct wavelengths that are created. We don't have all the reds, all the oranges, all the yellows. We don't have Roy G. Biv. We have very individual, definite wavelengths that are formed. That's interesting. So this light here is not white light. It doesn't contain everything. Not all of the wavelengths. It contains specific ones. And remember, these wavelengths are being created because of what? Electrons that are going from high energy positions to low energy positions. So they're dropping a certain distance and creating these different wavelengths. When you look at those different wavelengths, here are the wavelengths that are created. On this film strip or something in the back there that is then going to detect the different wavelengths, the different colors, we've got violet, this wavelength of violet, this wavelength of blue-violet, this wavelength of blue-green, and this wavelength of red. Those are the specific wavelengths that are emitted by hydrogen gas. The exciting, and then the energy is lost, but the electrons that are excited from the hydrogen gas. Here would be the spectrum, okay, the electron spectrum, or the light emission spectrum for boron. If we had a tube of boron here, we would see these different wavelengths. So these specific, there's 1, 2, 3, 4, 5, 6, 7, 8 it looks like. Okay? Alright, let's answer some questions here. Use colored pencils to color the hydrogen and boron spectral lines within their respective spectra in Model 2. Okay, you can do that if you want to. We have the colors that are given to us, so we'll just go with that. List the spectral lines for hydrogen gas by color and corresponding wavelength. So we have them right here. Violet, wavelength is given, blue-violet, wavelength, blue-green, wavelength, and red wavelength. They want you to, they're setting you up to understand that we have very specific wavelengths created when light is emitted from excited hydrogen gas particles. Number 9, the spectral lines for boron were produced using the same method as hydrogen. List 3 of the colors and corresponding wavelengths of boron spectral lines as its light passes through a prism. So you can name any one of the 3 that are listed right there. All right, let's talk specifically about the hydrogen spectrum in Model 2. Which color of light corresponds to the shortest wavelength? So shortest wavelength, remember, would be your red one here. Okay? Oh, sorry. I apologize. Shortest wavelength would be the violet. Okay, right there. The violet is 410. The longest wavelength would be your red. Which color of light corresponds to the longest? That would be your red. And just to remind you, this means violet is high energy, this is low energy, short wavelength is high energy, long wavelength is low energy. Again, with the hydrogen, which color of light has the most energy? So we just mentioned that. Higher energy, shorter wavelength, so that would be your violet and your red. Okay? Alright, let's move on, and in question number 12 it says, does a gas discharge tube filled with boron emit the same wavelengths of light as a tube filled with hydrogen? And the answer is no. Here it is for hydrogen, you got 4 distinct wavelengths. Here it is for boron. So you have different wavelengths emitted. Yes, do you have violet? Yes, you've got some violet. In fact, you've got about 3 different shades of violet there. But they're at a different wavelength, 412, 420, 424. The violet for hydrogen is 410. Yes, you've got some blues, you've got some blue-greens, you've got a red, but they're different wavelengths. Hold on, we're going to talk about why that's significant to the structure of the atom and specifically to electrons. Does a gas discharge tube filled with, we already got that. Okay. The spectral lines for atoms are like fingerprints for humans. Spectral lines for atoms. Every atom, when it's a gas in a tube and the electrons get excited and then they lose energy, they're going to emit very specific wavelengths. So it is kind of like an identification. How do the spectral lines for hydrogen and boron support this statement? So hydrogen has very specific wavelengths that it emits, and boron has different wavelengths. So if you were to see these wavelengths, let's say you had light coming from a distant star, and you were to see this collection right here, this collection of wavelengths in the light that you have coming from a distant star, you might conclude that there is hydrogen in that sun. Okay, so you might conclude that hydrogen is a part of that star because of the wavelengths that are coming from that star to our Earth that we were able to detect. Circle the appropriate word to complete each statement. So electrons and protons, they are going to repel each other. As an electron gets closer to the nucleus, the attraction to the nucleus gets stronger. So as they get closer, the attraction is going to get stronger. Remember, we talked about that with Coulombic attraction. The closer they are together, the stronger the force. For an electron to move from an energy level close to the nucleus to an energy level far from the nucleus, it would have to gain energy. So think of it, if you've got your nucleus here, and you've got protons in that nucleus, and then you've got an electron, and if they're close together, that is a strong force. That's a strong force that is keeping those two together, because they're close together. If you want to move this electron further away, then you're going to have to exert some type of force on it. There's going to require work. So to move this electron further away is going to require work. Energy. Okay? Energy is going to have to come into play. It's going to have to gain energy in order to do that. For an electron to move from an energy level far from the nucleus to an energy level close to the nucleus, it would have to then lose that energy. So if up here it took you work to get that up to a further point from the nucleus, and then it comes back down, it is then going to give off that energy in some form or another. Okay? It's not unlike gravity. Okay? If you had an object and you wanted to lift that object up in the air, it's going to require work. You have to put energy into that object. And then if you drop that object, it is going to release that energy. Okay? That potential energy in that case. It's going to turn into kinetic energy, but here you're going to give it more potential energy, this object. If you drop it, then potential energy is going to decrease. It's going to lose that potential energy. By the way, when it loses energy, it's not going to just disappear. That energy gets transferred or transformed into a different kind of energy. So in my gravity example, this potential energy gets transferred into kinetic energy. Okay, it goes from potential energy into kinetic energy. In our nucleus, the energy that the electrons gain is going to be lost, and the lost energy then is transferred into that light, as I mentioned before. Okay? All right. So there's a scientist a while back, Mr. Bohr. He modified Rutherford's nuclear atom. So these two scientists were looking at what do they think the atom looks like. Obviously they couldn't see it, but what does it look like? They were using what they knew, their knowledge, to try to come up with a model for what the atom looks like. So Bohr took this other scientist's model, Rutherford, and he used that in order to try to explain how light interacted with the electrons in an atom to produce spectral lines. His model included electrons orbiting the nucleus at specific energy levels. Electrons absorb energy from various sources, electricity for example, in our example there, in our models. When they move from lower energy levels, which is called the ground state, to higher energy levels, which are called excited states. Energy is released as electrons return to their lower energy levels. So, because of the spectral lines that are emitted from excited gas particles, scientists concluded that if there are specific wavelengths that are being created, that must be a result of electrons falling from specific distances. Not every wavelength is created. So an electron can't just fall from here and then just a little bit down below it and emit and just keep, minuscule steps, take tiny little steps as it drops from every wavelength through the possible different options. It's not doing that. It's going a specific step down. So it is stepping from this energy level all the way down to another one. That drop corresponds then to a release of a specific amount of energy. And that specific amount of energy is then going to correspond to a color of light that has a specific wavelength. So they said, then these electrons must reside at specific energy levels, and they are going to call them orbitals. Okay? Orbitals, kind of like they're orbiting around the sun. Now, as we'll see later on, that's not exactly what electrons are doing, but the name stuck. So, let's say that we have here the nucleus. The black dot is the nucleus of your atom. And then these concentric circles are the different energy levels that electrons are going to reside at. They cannot hang out in between. They reside at specific energy levels, and that's it. And this would be unique for a particular element. Every element is going to have its own arrangement of energy levels. And those electrons are going to reside at those specific energy levels. And when they move between those energy levels, they're either going to gain energy from some source, or when they drop down, they're going to emit light at a specific wavelength. Okay? So, is energy absorbed or released for the electron transition shown in the diagram to the right? So if this is an electron going from energy level number 2 up to energy level number 5, it's going from 2 to 5. In order to go from low energy to high energy, it has to gain, has to absorb. Okay? Gain or absorb energy, absorb energy to go from low energy to high energy. Where does it get that energy? From some outside source. Like our example was electricity, or maybe heat. Alright, now we're going to look at a model, specific model for the hydrogen atom. And we're going to look at what happens when electrons go from one energy level to another energy level. We have several different possibilities, A, B, C, and D, and you'll see that here an electron is going from energy level 6 to energy level 2. Here it's going from 5 to 2. Here it's going from 4 to 2, and here it's going from 3 to 2. And notice, for every drop from a particular energy level to another energy level, there is a specific wavelength that is emitted. They're not all the same. This is emitting a specific wavelength, and that's going to be a certain color. This is emitting a different wavelength. This one is emitting a different one, and every different wavelength is going to correspond to a different color. So this is unique for our hydrogen. Remember back up in Model 1, we saw that hydrogen had 1, 2, 3, 4 different wavelengths emitted in the light. Once it was split up, we saw 4 different wavelengths. Okay? So we're going to kind of isolate those different wavelengths as we look at possible different drops from energy levels for an electron. All right, identify the drawing in Model 3 that depicts a hydrogen atom with an electron moving from energy level 5 to energy level 2. All right, so 5 to 2. So we kind of named that right here. Oh, here it is. So that would be B. So this is going to be B. B is going from 5 to 2. Refer to models 1 and 2 for the following questions. Label the picture with n equals 5 to n equals 2 and list the corresponding color of the light emitted. Okay, label the picture. This is n equals 5 to n equals 2. And the corresponding color of light. Well, how do we know what color of light it is? Well, let's look here. We have 4 options, 4 different diagrams in Model 3. Remember, we had 4 different wavelengths back in Model 1. So, if this is the biggest drop, this is the most energy, high energy. And remember, high energy means short wavelength. This must be the shortest wavelength. And this is the longest wavelength because it's a very short drop. This is low energy. Long wavelength. And then these others are in between. So this is the next longest one, and this is the next shortest one. Okay? So we should be able to identify what colors these are because we're going to go back up here and identify the colors that were given to us. Violet, blue-green, and red. So violet, this must be our violet. I think I'm getting ahead of the questions. This must be our blue-violet. This, I think it was blue-green. And this is our red. Okay? This electron transition, it is going to meaning this one here in B, is going to release energy. Releases energy. This electron moves from a higher energy state to a lower energy state. And is light absorbed or released in the electron transition? Well, light is going to be released. It's going to be emitted as a result of this electron dropping from 5 to 2. What light is emitted? Blue-violet, because we identified that up here in Model 1, and it's going to have a wavelength of, it's going to have a wavelength of 434, okay? I think that was nanometers, right? Okay. Label the remaining drawings in Model 3 with the electron transitions that are occurring, the wavelengths, and the corresponding colors as given in example A in Model 3. See Model 2 in order to identify the color of spectral lines produced in each of the hydrogen atom electron transitions shown in Model 3. And if you want to, you can color them. Okay? So, we would continue to do this. This is going from n equals 6 to n equals 2. This one is n equals 4 to n equals 2, n equals 3 to n equals 2. So this one is your violet, and it had a wavelength given to us up here of 410, 434, 486. Let's see if we remember those. 410, 434 we had already. This one is 486, I think. And the red, the red is 656. Okay? Alright, so now here's the deal. I need to explain this because you need to understand that all four of these lights are being emitted when hydrogen gets excited. It's not like you just see violet, or you just see blue-violet, or you just see red. It's the mix of those. And so the unique combination of these four wavelengths and these four colors are going to give excited hydrogen gas in that tube a kind of a purplish look. All right? You won't see these individual colors unless you separate them. So it's a combination of all of these. And this is happening, I mean, there are millions and millions of atoms and electrons in that small tube of hydrogen gas. So this is happening constantly. So you have constantly electrons that are being excited and then lose their energy, excited and lose their energy. And they might go all the way up. They might get so much energy they go all the way up to 6 and drop down to 2. They might only go up to 5 and down to 2, or 3 down to 2, 4 down to 2. Okay? So that's why you've got all these different color options here. Consider the electron transitions in Model 3. Which of the electron transitions involves the most energy? Well, most energy has to do with the shortest wavelength. High energy, short wavelength, violet. And that's because you can see it has the longest drop. Longest drop means most energy is emitted. That would be from 6 to 2. Explain why this transition involves the most energy based on your understandings of the attractive forces between the electrons and protons. So the idea here is that if you're going from energy level of 6, there's 5, 4, 3, 2, 1, and then the nucleus, it's just a farther drop. So if you go just from 6 to 5, this electron has to maintain some energy in order to keep its distance from the proton. Remember, it's attracted to the proton. So there must be some energy that here at level 5 that's still holding it at that position. But if a bunch of energy is released, and it is just set loose, it's just able to just go all the way back here as close to the nucleus as possible, then lots of energy is going to be released when it travels that entire distance closest to the proton. Okay? So it's going from, if you think about the forces, here, way out here, this is a weaker force interacting between the proton and electron, and if you then come in close, this is a stronger force that's going to be holding them together. So the difference there is going to tell you that you have a large energy change. A large energy change if you're going from very weak to stronger when you go from far away to closer. Okay? Explain why a single atom of hydrogen cannot produce all 4 hydrogen spectral lines simultaneously. Okay? So why a single atom simultaneously? Well, that's because hydrogen only has 1 electron. And so if you've got 1 electron, that 1 electron can only go up to a certain energy level and then drop once at a time. Okay? So it goes up, it would drop, it would emit a specific wavelength. Then we get excited again, drop, and emit a specific wavelength. But that's not what happens in that tube of hydrogen. It's got millions of atoms. So all of these atoms, some of them are emitting violet, some are emitting blue-green, some are emitting red, some are emitting the blue-violet, and you've got a mix of them. Okay? And that answers question 23. How is it that we can see all 4 colors, or the mix of all 4 colors? And that's because you've got millions of hydrogen atoms in the sample of gas. Okay? Alright, let's see here. Our extension questions. Oh, we love extension questions. Let's look at these and just expand our knowledge just a little bit as we talk further about our electrons and the emission light, the spectral lines here. Alright, question 24 says the hydrogen spectral lines in Model 2 are only the wavelengths of light that are in visible range and therefore seen. What they're saying is visible light is a very narrow range of wavelengths. Other electromagnetic radiation is going to have other wavelengths, but we can't see that with our eye. So you may have been wondering, well, what about all the other possible combinations of drops here? What if it dropped from 6 to 1? What if it dropped from 2 to 1? Or what if it dropped from 3 to 1? Or something like that? Aren't those possible drops so that something is emitted, some type of light is emitted? Yes, most certainly. But they may be emitting an electromagnetic radiation that is not a visible light wavelength, the one that we can see with our eye. It may be outside of the range of visible light. It may be a wavelength that is lower or higher than the range of visible light. So, you can have special equipment to detect those wavelengths. So propose a hydrogen-electron transition that involves light with a wavelength in the ultraviolet. You can't see ultraviolet light. UV range, okay, from 10 to 400. Now that is shorter than any of the 4 visible wavelengths that we were talking about earlier. So if it's going to be a short wavelength, then it's going to have to be high energy, and if it's high energy, it has to have a longer drop. So it's got to go from 6, remember the drop we had before was 6 to 2, then it's got to go 6 to 1. Okay, and then that's going to emit even a higher energy wavelength, which would have a shorter wavelength, but we wouldn't be able to see it because it would be in the UV range. Okay? Alright, B, propose a hydrogen-electron transition that involves light with a wavelength in the infrared. We don't see infrared either. That is on the other side of red. And that is a longer wavelength here. So we've got red IR. So let's look back up here. If our shortest drop for red was right here from 3 to 2, then maybe we would want a shorter drop here. And if you look at these, maybe the shortest drop would be, and these are kind of proportional to the amount of energy that is released. In other words, the distance between these energy positions. So you might want a short drop. a short drop like this, 6 to 5, or 5 to 4, looks like that's a shorter drop than 3 to 2. Even maybe 4 to 3, but you wouldn't want anything greater than the distance between 3 and 2. You couldn't say 2 to 1, that looks like it's a little bit bigger. Okay? So you want a short drop. You could say 5 to 6, or sorry, 5 to 4 I said, 6 to 5, okay? Maybe even 4 to 3. All of those might be shorter than 3 to 2 and give you a, a lower energy wavelength that would be longer than just red. It would be in the IR range here, okay? So we said 6 to 5 or 5 to 4 or something like that, okay? Okay, number 25, below are diagrams for the bright line spectra of 4 elements and the spectrum of a mixture of unknown gases. What they're saying is here, if you had lithium gas and it was excited in a tube by electricity, and then you saw the light, you analyzed the light that's being emitted, you would see this wavelength, and this one, and this one, and this one. And they're not even telling you specifically what those are. They don't have to. We don't really, we're not looking at them and trying to determine what color or wavelength. We just are going to register them on our sheet that's detecting the wavelengths, and we're just going to keep record of them. Here's for hydrogen. Here are the 4 for hydrogen. Here are the ones for helium. 1, 2, 3, 4, 5, 6. And then we've got sodium. 1, 2. And now we have this unknown mixture of gases. All right? The mixture of gases here, down here, we don't know what's in that container. All we do know is the wavelengths that are being emitted. We have the spectral emission results for that unknown mixture of gases. Which element or elements are not present in the unknown? Well, if it's not present, we know it won't be present if the wavelength from that known gas is not visible, is not present in the unknown. So all we have to do is find one of these wavelengths up here from lithium, hydrogen, helium, or sodium that does not appear in the unknown. And we would know that that gas is not there. And if you'll notice, lithium, we go straight down, oh, it is not there. That lithium wavelength, whatever that is, does not appear down here. It's missing, so we know that lithium is not in the unknown mixture of gases. Which element or elements are there? Well, we have helium, because every helium wavelength is also in the unknown. Every hydrogen one is also in the unknown. And every sodium, oh, I take that back. The sodium, there's this one and this one. This here is probably here because of the helium, not because of the sodium. So sodium is not there as well, and it's only the hydrogen and the helium. Model 2 shows the emission spectra for hydrogen and boron. Scientists can also record the absorption spectra for elements. Propose how this might be done and what the absorption spectra of hydrogen and boron would look like. The absorption spectra would simply be, instead of light being emitted, it would be what light is being absorbed. Okay? So all that means is that you would have light, instead of detecting what's being emitted by the excited gas, you would then figure out what is being absorbed. How would we accomplish this? Well, we would have our tube of gas. This is the gas in there, hydrogen or whatever. But instead of exciting the gas and then having it emit light, we would take white light and we would shine white light through this gas. And all of the colors would pass through here except the 4 that are part of hydrogen's emission line spectrum. Okay? So, in this case, what you would see is you would see like a rainbow of colors here, but then you would see 4 specific places where it's dark. And that's because those are the four wavelengths where this white light is being absorbed by the gas instead of being emitted by the gas. All the other colors would pass through, but it'd be those four distinct wavelengths for hydrogen, and those wavelengths would be absorbed by the gas, and they would appear as black on your detection screen back here, and all the other colors you would see. You would see all the other colors here, except for those four wavelengths would appear like a black line. Okay? So I hope this was very helpful in you understanding a little bit about how light, the behavior of light, and these specific experiments with tubes of gas being excited, how those experiments helped us understand a little bit that electrons reside at specific energy levels. So you have to understand that those electrons are at those energy levels and only at those energy levels. They can't be in between. And those energy levels are unique for every atom. Every atom is going to have kind of its own arrangement of energy levels as far as the distances of those energy levels. We are going to talk later on about those energy levels. We're going to call them orbitals because, yes, we know electrons don't orbit around the nucleus. We understand that, but that name kind of is held over from earlier models. Those orbitals are basically going to be areas where electrons reside. And those electrons are understood to be residing in specific areas. High probability that you're going to find them in those areas. And then only in those areas. So in order to move up to a higher energy level, the electron's got to gain energy. When it drops down to a lower energy level, it releases that energy, most likely in the form of light. All right, we'll see you in the next video.